All right, so let's get started. All right, so we were looking at support vector machines. What we did so far was we saw how support vector machine learning is done. Right, follows the principle of maximum margin. This is a figure that you have seen before, and then we saw that the optimization function has constraints. So we looked at the method of the method of Lagrange multipliers to solve that problem. And then we also looked at the dual formulation. The reason we looked at the dual formulation was that it allowed us to deploy kernel methods, right? Because every data object in the dual formulation appears as a inner product, right? So we can replace that by a kernel function. One more advantage we saw with that formulation was that most of the Lagrange multipliers, those alphas, become 0. So any alpha corresponding to a data point which is not on the margin is 0, right? Which meant that we can compactly store our support vector machine and make it very efficient, because now when you get a new data point, right, if you remember this, to get a prediction for the new data point, you would have to solve this, well, compute this quantity, right? So this is a summation, right? This goes from 1 to n, where n is the size of your training data, right? So let's say n is million. In that case, what you would do is you will look at your alphas which you learned from your QP solver, right, and then multiply it with the true label, multiply it with the data point, and so on, right? So you have to do this a million times. But what happens is that because of the property of these alphas, right, because of that KKT condition, most of the alphas are 0, right? So this summation does not go from 1 through 1 million. It only runs for those alphas which are not 0, right? So that makes it very efficient in that sense. Right? And also the fact that you have an inner product means you can use kernel functions. So anyway, so that's the whole story behind support vector machines, right? However, what we have seen, what we have assumed so far is that the data is linearly separable, which means that yes, there is a potential to draw a line here, right? However, in practice, data might not be linearly separable, right? That's a more what should I say, a more realistic setting where data is not linearly separable. So it turns out that you can still learn a support vector machine, but you'll have to change a few things. All right. So what you do is you introduce some flexibility, some relaxation in your constraint. So remember, in your original constraint, right, you had this as the constraint, that for you want to learn a W such that and B such that this quantity is true, which means that all the data points should be on the right side of the differentiating plane, as well as they should be away from the margin, right? So that was the idea. But when they are not linearly separable, you relax it, right? You allow some examples to be misclassified, right? They could be on the other side, and you also allow some examples to fall inside the margin, which means that you could have it means that it is okay to learn a line in which some of these blue points are either here or on this side of the hyperplane, and some of the red points are over there. So you allow for some training error, right? Then comes the question, how do you now solve this optimization problem? So the way, so this kind of tracks what we had looked in perceptron, right? Remember, in perceptron learning, if the data was linearly separable, then you had a very nice algorithm. There was no optimization there, right? But when the data was not linearly separable, then we introduced this notion of a loss, and then we came up with an algorithm that minimizes that loss, right? The same thing here. So the way you introduce this flexibility is by introducing this notion of slack, right? So slack means that it is okay for some point to be misclassified, to be inside, right? So the idea there, so again, right, in separable case, this is the strict condition, which meant that whatever W you learn will have a 0 training loss. But if there is no line to be learned, right, then this optimization function will never converge, right, because it will try to find that line which does not exist. So what you do in the non-separable case is that you introduce this value. What is this again? Chi, I think, right? Chi. Okay, let's call it chi. So for every data point, you introduce a variable called chi. So chi n. It has a subscript n because you have one chi for every training data point, right? And then you say that you do not want this constraint, this is too strict. You want to learn a W such that it is sort of close to the margin but away. I mean, you are ready to accommodate this error. All right, so this is called a slack variable. So of course, when you do your gradients this week, there's one problem in which you have to compute the slack for every data point. So the slack basically says how far are you away from the correct from the decision boundary, right? How far? So if you are on the right side of the decision boundary, on the correct side, then there is no slack, right? You're not paying any penalty. But if you're away, then you're paying some penalty. So which means that if you are misclassifying, then this should be greater than 1. So this is what will happen. So for example, this is the correct, let's say this is the decision boundary, right? So slack for all of these blue points which are on this side of this dotted line, which is the margin, will be 0 because you're on the right side. When you go here, there will be some slack. It will be greater than 0. And when you go out, I mean, when you're misclassifying, then the slack will actually be greater than equal to 0 or greater than equal to 1. All right. So now we have to see how to learn a W with this, right? So what we are saying is it is okay to have some misclassified training examples, but you do not want all the examples to be misclassified, right? So the slack should not be unconstrained, right? You could definitely learn a training, you can definitely learn a line which is anywhere and everyone will have some positive slack, but that's not what you want. You want to allow some points to be misclassified, but you still want to control this slack, right? So you want to minimize the number of examples which have some non-zero slack. So now the optimization problem becomes slightly different. Well, so if you look at it, it looks very much like the separable case, except that now you are trying to find a W and a V such that the margin is maximized, right? Typically we also write a half here, but that doesn't matter too much, right? So you want to maximize the margin, but you also want to, oh, I'm sorry, this should be minimized, right? Because we have a minimize here. So we want to minimize the margin, right? Sorry, maximize the margin, which means that minimize this quantity. Plus you want to minimize the sum of the slack. So you don't want to accommodate too much slack, right? So you want to, so it becomes like a you're trying to optimize over two quantities, right? And both of them, and I'll show that to you, kind of work against each other. So it's kind of a joint optimization problem. You're trying to minimize the slack as well, total slack, as well you're trying to minimize or maximize the margin. And then the constraints become slightly different. See, earlier the constraints were that all your data points should be on the correct side of your margin, right? But now you are ready to accommodate some slack. So you said every data point can be away from the margin or on the wrong side of the margin by just chi of n, right? And but then you want to minimize the total sum. So that becomes your total error, right? So there is a constant here C, which kind of controls the impact between how much you want the margin to be maximized and how much slack you want to introduce, right? So I'm going to give you an example. Let's see. All right. So let us assume that we are trying to learn a kernel SVM, which means that it would learn, let's say just for the sake of example, the kernel is a polynomial function. Kernel is a polynomial, okay, so of degree 2. So which means that you're trying to learn quadratic boundaries, right? So let us assume that our data looks like this. So these are all my positive points over here, and these are all my negative points over here. Okay, so if we do not introduce this notion of a slack, right, then what will happen is that you will end up learning something like this, right? Because you try to I mean basically you want a surface, and the reason this surface is no longer a line is because I'm using a polynomial kernel, right? It will look like this because it will try to make the training error 0, right? But so which basically means that This was your, right, which means that C is equal to 0. That means you're not, no. Well, actually C is very high. C is high. That you're not allowing any slack at all, right? Which means that if you allow any slack, the penalty that you have to pay in your objective function will be very high, right? So let us C is very high, which means that the solution will be such that there is no slack at all, right? But if C is very low, so this is for if C is very high. If C is very low, then it is okay to have some slack, right? It is okay to have some slack as long as this margin is maximized. So in that case, what it will do is it will try to learn a line, maybe a more straighter line, and it's okay to have some misclassification because C is very low, right? So that is sort of the trade-off. So in your programming assignment 3, you have to explore the sklearn SVM, which is the implementation of SVM in that Python library, and there I want you to explore the effect of C, right? But the basic idea is that C controls sort of the trade-off between how simple your surface will be and how much training error. So it's kind of a regularizer, right? So C is nothing but a regularizer. So if you remember our discussion in ridge regression and even in neural networks, right, we used to have that lambda, which helped us control how simple your decision boundary has to be and how much training error you're willing to accommodate, right? So here it has the same effect as lambda in ridge regression, or similar effect, right? So if you increase your C, it will try to learn something that it really tracks the data, so it might overfit, right? So it has the same bias variance trade-off aspect to it. Any questions so far? All right. So after this, I'm not going to go into it too much. The point being that when you look at this problem, right, this also is a constraint optimization problem, right? You can and it has all these inequality constraints. Now you can use the same Lagrangian approach to bring all of these up here, which means that you introduce all your Lagrangian multipliers, alphas, right? And then you can turn it into a dual formulation, and then you can solve that. You'll get your alphas, and everything is still the same. The weight that you will get can be computed from those alphas, right? And then you can use it for your prediction, right? So everything else holds same, except that there is a notion of a slack here. The only thing that will change, and it will still have everything as dot product, so you can use kernel methods, but the only thing that will change is that your support vectors are points for which alphas are non-zero, which means, see, earlier in the non-separable case or in the separable case, the support vectors are the points that lie on the margins, right? But in the separable case, the support vectors are points that lie on the margin, that are inside the margin, and which are on the wrong side of the hyperplane. So here, these 2 points will be the support vectors, these points will be the support vectors, and these points. So you have more support, and this blue one, right? So all of these points will be the support vectors. So somebody was asking earlier, last class, that for a linear case, you might not have too many support vectors. So in a, yes, go ahead. Oh, you can't see it at all. Sorry. I was just testing how much you're paying attention. All right. So, what do I have to explain again? All right. So let me say that again. So this is the optimization formulation, as I said, right? So what it turns out that you could use the same approach to solve this optimization problem, which is that you convert all of these inequality constraints, put them here, make it a Lagrangian formulation, right? And introduce n Lagrangian multipliers, which are alphas, right? And then you can convert it into a dual formulation, solve for alphas, and then you get your weights. Weight will just be like this, right? So it is very similar to the separable case. What will happen is that all of your x's will still occur as inner product, so which means that you can still use your kernel methods, right? The only difference that will happen is that the number of support vectors, which means the number of data points for which alpha is greater than 0, will increase, right? So in the case of separable, what we said was that only those points that are on the margins, this one, this one, this one, and this one, will be the support vectors, because only for these points alpha will be greater than 0, right? For all of these other points that are on the right side, the alpha will be 0 because of the KKT condition number 5. But in the case of non-separable case, the alpha will be non-zero even for these points. So these are the points which are on the wrong side of the margin, 1, 2, 3, 4, and 5, right? So these will also be your support vectors. So which means that the number of support vectors that you will have will increase a little bit, right? They will be more than just what you would get for a separable case, but they will still be fewer than the whole data set. So you still get all the benefits of kernel methods, of very few support vectors and everything, right? So so this is essentially a quick discussion of non-separable support vector machines. Any questions so far? All right. So so let me just recap some, provide some concluding remarks. Okay. So SVMs are fairly widely used in the community. The reason being, number one, that they do all this kernel thing. They're pretty efficient, right? Of course, if you look at the training time for SVM training, right, or the time for SVM training, it's roughly cube of training data, so which is still not very efficient, right? So when I say the training time, which means that if you, where is that, right, this you have to solve this dual formulation, right? So this formulation has n constraints alpha, right, and you try to solve it, and it typically takes n cube time, okay, which is for very large data sets not very good, of course, but then a lot of people have done a lot of research to make it more efficient. So if you look at some of the packages that are out there, they do a lot of tricks and a lot of optimization to make it fast, right? So so there are approximate QP solver, there are online training methods which can sort of handle large data sizes. And as I said, the reason SVMs are so powerful, one of them is because they allow all these kernel tricks. So it's a classic case of a kernel machine, right? So it allows learning non-linear boundaries. Fantastic. You can also extend it for multi-class classification. All right. So in your assignment 3, you are looking at logistic regression for a multi-class case, right? So you can do the same thing for SVMs as well, and you can also use it for regression. So cases where y is not a binary label. So far we said that y is +1 or -1, right? But y could also be a quantity. So just like linear regression, you can predict some value, okay? And we will not go into how to do that, but that kind of a model is called support vector regression. So what happens is now you can learn nonlinear sort of curves that fit data using support vector regression. The only thing that changes there is that instead of this constraint, the constraint becomes a little different, because now you're not trying to put points on the right side of the boundary, you're trying to fit points on a line or a curve, right? So this error becomes slightly different, but other things still hold. So support vector, so whenever you get a support vector machine package, right, you would typically get both classifier and regression. And then there are many more extensions of support vectors as well. All right. Any questions so far about support vector machines? Great. All right. So this kind of concludes our discussion on support vector machines, but I'm going to talk about it a little more. So the last thing that I want to discuss in this linear model kernel machine thing is I'm going to discuss all of them together. All right. So we have looked at how many linear models so far for classification. We have looked at perceptrons, right? We have looked at logistic regression, and we have looked at support vector machines, right? All of them have quite similar form, right? All of them has a weight vector W, and you do an inner product with your data vector, which is X, and then you use that to compute, to do the prediction, right? So in fact, all of them are kind of same, right? So for a perceptron, you look at W transpose X. If it is greater than 0, you call it +1, less than 0, -1. Same thing with support vector machines, and kind of same thing with logistic regression as well, because you compute W transpose X, then you convert it into a probability by doing sigmoid of that. But the core part is the same, right? The part where they actually differ is how they learn that W, right? So we have looked at three ways to do that: support vector machines, perceptrons, and logistic regression. So their prediction part is kind of same, W transpose X or W transpose X plus B, but their learning part is different, right? So in general, if you're trying to learn this linear model, right, what we typically do is that we have some training data, right? X is the data, Y is the label, Xn and Yn. We define some loss function, right? And then we define some regularizer because we want to keep it simple. And then you solve, you find W and B which minimize this. So this is a general form of any linear model, right? And typically what you want is you want a W and B which minimizes this error. So let's look at this error, right? So this error, I is an indicator function. Indicator function means it is 1 if this inside argument is true, and 0 if it 1 if it is false, and 0 if it is true. What does this say? 1 if this is 0, 0 otherwise, right? So, or false. So which means that it gives a penalty of 1 if you make an error and penalty of 0 if you don't, right? So essentially you want a W and B that minimizes this. Basically you are trying to minimize the number of errors that you make on your training data, plus you want to regularize it as well. All right. But the problem is this loss is what we call 0-1 loss. So if you are correct, then your loss is 0. If you are wrong, your loss is 1, right? So ideally this is what you want to minimize on or optimize for your solution. But it so happens that minimizing these kind of losses is very hard, right? Because this is not a smooth loss function. This is what we call a step loss function, and I'll describe it later, right? So what all of these three different models do is they try to simplify it so that they can use some optimization formulation. All right. So again, let's just focus on the loss, right? Let's say these are the, what is this pencil? Linear models, right? So the loss, the ideal loss that you want to minimize on is over all data points, this indicator y, yn W transpose xn plus b is less than 0, right? Which means that you want to penalize a misclassification by 1, otherwise 0. But these losses are very hard to optimize because this is a 0-1. This is like a step function, so it goes like this. So you can't really write a gradient descent method to sort of solve these kind of losses. Gradient descent needs more smoother sort of these curves, right? So what all of these different methods do is SVM, logistic regression, and perceptrons, is that they change this loss function in different ways, right? SVM does what is, and I'm going to explain it, but the loss that SVM looks at is called hinge loss. The loss that logistic regression looks at is called log loss, that you are familiar with, right? And the loss that perceptron looks at is called the squared loss, right? So the squared loss, so if you look at one data point, one training data point, the loss that this looks at is it's yn W transpose xn plus b, or yn minus of this, right? So it says if it is less than that, this quantity, then you pay that penalty, and I'll explain a little more of that. This of course is easy to see. This is basically log of the true y minus W transpose xn, log of that, and this is squared loss, which is y minus W transpose xn squared. So these are all three different losses, right? And that is why these three different methods are different. Basically they are using different losses. All right, so let's look at these losses a little more. So what is the difference between all of these loss functions, right? So these loss functions are what we call together surrogate loss function, which is the reason we call it surrogate is that the actual loss that we want to minimize is this. This is the 0, 1 loss, but it is hard to optimize on. So that's why we replace it with some functions that are easy to optimize on. I'll show you those functions as an illustration. So let us consider one data point, okay, one training data point. Let us consider x and yn, one data point, and assume that yn is positive. All right, which means that it's a positive data point. Now let's look at the 0, 1 loss. Okay, so let this be the loss dimension, and this is your prediction, predicted y. All right. So the 0, 1 loss says that if you have predicted y to be less than 0, right, then your loss will be 1. And if you have predicted it less than greater than 0, then loss will be 0. Right? That is this graphically, right, for one yn. So it doesn't matter how big your prediction is, as long as it is greater than 0, you call it 0 loss, otherwise 1 loss, right? That's a 0, 1 loss. What hinge loss says is that if you predict something greater than 1, then your loss after that is 0, all right, but otherwise it gives loss like this. So this plot, use different color here, this plot, this is called hinge loss. Okay, this one was 0, 1 loss, and this is basically looking at the loss function. I mean, in SVMs we don't really optimize our loss, right? Our loss is actually in the constraints, but the loss that you pay looks like this, right? The slack, that sigma, that chi n is 1 minus of this thing, which means that if your prediction is 1 or more, then you pay no penalty, right? That means you're on the right side. But if your prediction is less, then your penalty, less than 1, penalty goes up like this. If it is 0, right, if your prediction is 0, which means that you're on the surface, then you pay a penalty of 1, and then your loss increases like that, right? Now let's see, what does the squared loss do? The squared loss, what it will do is that it will pay a penalty which is y minus the actual value square, right? Which means that that thing will look like a, so at y equal to 0, when your prediction is 0, you will be paying, because this y is 1, right? So you'll be paying a loss of 1. When your prediction is actually equal to y, then you will be paying a loss of 0, right? And everywhere else it will have a sort of a squared effect, right? Because it's a parabola. So this is what we call squared loss. All right, so this is squared loss. And then the last one is the log loss, right? So log loss, of course, at when you make your prediction to be 1, then the loss will be close to 0, right? And then everything else will be will go like this. So that one will have like a log, it goes like this, I think, and that tends to 0. So this is what we call a log loss. So the point behind this graphic, this very ugly plot that I have drawn here, is that the true loss that you want to optimize on is a 0, 1 loss, but it is hard to optimize on. So what we do is, all of these different methods, they use a surrogate loss function which have different shapes. So hinge loss has shape like this, log loss has a shape like this, and squared loss has a shape like this. All right. So if you follow some of the literature in learning theory, in computational learning theory, they analyze these loss functions and say, okay, which one is better, which one is not better, which one is poor. All right. It turns out that perceptron loss is not a very good loss function to use. Why? Because it sort of gives you some error here, and then it's going up like this. So it does not approximate this function very well. But these other functions, the hinge loss and the log loss, approximate them in a slightly bit better way. But that's sort of a more advanced topic that I do not want to go into. But the basic idea is that these different classifiers that we have seen so far use different versions of loss functions, and they sort of look like this. All right. So tomorrow, if you go out and say, I'm going to write my own classifier, a linear model, right? What you can do is you can come up with a different loss function, which of course is not this, because this will be hard to optimize, but some loss function that you think would work okay, right? Which means that it should be able to approximate this 0, 1 loss in some way, and then you will have to come up with an optimization method to optimize that loss, right? So in the case of squared loss, we used gradient descent, right? In the case of log loss, also we use gradient descent because both are smooth. In the case of hinge loss for support vector machines, we did not use gradient descent, right? We use something called quadratic optimization, right? And then there is this other thing, which is regularizer, right? So we have talked about loss, which is here, the training error. But this part is where we say we do not only want to minimize our loss, but we also want to keep our solution simple. So that's why we bring this regularization term, which is typically accompanied with a scalar value, which is lambda or c in the case of support vector machines. And the idea is that the reason we need it is we want to ensure simplicity, right? Now, the ideal regularizer that you want would be some regularizer which only selects some of the features, some of the attributes, all right? So most entries in this vector should be 0. So this is the kind of ideal regularizer. You want a regularization function in which penalizes any non-zero quantity, and so it tries to minimize the number of non-zero quantities you have. But again, since this has this indicator function, that means that this whole function again becomes like a hard optimization problem, because this is sort of a step function, right? Again, indicator functions are all steps. So what different methods do is they approximate this with some surrogate regularizer, all right? So we have seen different regularizers. We have seen, of course, our favorite L2 node, right, which we use for ridge regression. You can use it for other things as well. Oh, in fact, for support vector machines, this is the regularizer we use, right? That's W transpose W. In the case of, you can also use something called L1 regularization, which we have seen in Lasso, right? We saw it in the context of regression, but you can use it for ridge regression, for logistic regression as well, right? So there you are trying to use this function, or in general, you can use any other norm or something else, right? So the idea is that ideally you want this regularizer, which basically gives a penalty of 1 for every non-zero quantity, every non-zero entry in your weight vector. But this becomes hard to optimize on, so we use some other easy to optimize functions, right? All right. Any questions so far? Yeah. Oh, no, you choose one of these. Oh, no. So what happens is that when you come up with a classifier, you make a choice that this is the loss function I will use. And the reason you do that, I don't know the exact reason, but there is some theory behind which is a better loss function. So you can use hinge, you can use squared, you can use log, or you can come up with your own. You can say it is y minus x W transpose x raised to power 3, right? And call it the cubic loss. But it might work well, it might not work well, it depends, right? You could come. Not necessarily, it depends on the data as well. But it turns out that squared loss is not very good. Between hinge and log, so this is basically trying to compare support vector machines with logistic regression, right? So there is no outright proof that says that support vector machines are always better than logistic regression. In fact, for your assignment, you have to compare these two for the digit data, and one might be better than other, but for some other data set, something else might happen. But in general, these are sort of good enough surrogate functions, plus they allow some optimization method to be implemented, right? You can come up with a really fancy loss function, but if you can't optimize it, then you can't really get a solution. There's another question somewhere? Sorry. No, if it's false, because you're paying a penalty. So whenever you make a mistake, penalty of 1, otherwise 0. Any other questions? Fantastic. All right, so that kind of concludes our whole discussion on support vector machines, on linear methods, and classifiers in general. In fact, this concludes our discussion on supervised learning. Right? I will, if someone is more interested in exploring more theoretical aspects of what we have discussed, I strongly recommend this book, excellent book, Statistical Learning Theory by Vapnik, who is sort of the inventor of support vector machines. But he also is sort of the V in the VC dimension that we sometimes use, right? The complexity of a classifier. So he has done a lot of work in this area. All right. Any other questions? Okay. So what we're going to do today is now actually change direction for the last time in a very big way. Part E. We are going to talk about a new type of learning now. New type of learning, which is called unsupervised learning. So far, the things that we have been looking at is what we call supervised learning. Why do we call supervised learning? Because they involve some training data, right? That training data provides some supervision. It says that, okay, for in the past, I have seen X's and Y's, and now you have to learn a model so that you can now predict the Y for a new X, right? So all follow the same approach, right? But there is another type of learning paradigm, which is called unsupervised learning, in which all you have is bunch of data, right? No labels, no Y, only X's, right? But you still want to make some sense out of it, right? So think of it like this. So if you have a robot, right, and the robot just goes out and observes many things, observes many people, right? So those are its X's. Now it wants to understand that without really having to predict something or classify them, right? So there is no label there. So that kind of learning is called unsupervised learning. And one of the learning methods, or one of the learning tasks, is what we call clustering. Okay, so clustering is nothing but taking a bunch of data and grouping them into some meaningful groups, right? So those groups are called clusters, and the task is called clustering, right? And I mean, as humans, we do that a lot, right? If I typically, we tend to group things together, right? We say, if I show you a list of 100,000 movies, you tend to say, okay, these all are similar movies. Maybe these are all comedies, and these are all whatever drama, and so on, right? So we have a tendency of grouping things together because then we have to store less data in our head, right? And we don't have to store entire data. We just have to store these descriptions of these groups, right? So if I give you a collection of 100 movies and nothing else, you maybe watch all of them, and then in your head, instead of remembering all of these movies, you might just remember, okay, there were 20 comedies and 20 dramas and 20 action movies and so on, right? So that task is what we call clustering. Now we want to come up with algorithms or software which can do this clustering in a computer program, right? So those are clustering algorithms. So let us look at that. So I'm going to motivate a little bit, but okay. So yeah, all right. So in general, clustering is essentially taking some data, grouping into different parts. Now, how do you group them, right? You have to group them such that each group, the points are similar, right? Or the objects are similar. You can't just arbitrarily partition them. That won't be a meaningful cluster, right? So that's the task of clustering them. So let's say, let me give you an example, and then we can sort of continue this discussion on Friday. So let's say you are a magazine editor. Let's say you're editor of Time. Yeah. Now you have to produce the next issue of Time, right? So what you do is you call your, whatever sub editors of different areas: politics, health, technology, sports, right? So let's say these are the 4 sub editors that there are in Time, and ask each one of them to send in K articles. So politics editor will send K politics articles, health editor will do this and everything. and then what you do is you just join them together, staple them, and that's your issue, right? So you can think of this magazine as a collection of these articles, right? So think of this magazine in which each article is a data object or a data point, which is not really a d-dimensional vector, but it's actually a document. But let's say we have some way of representing it as as a d-dimensional vector, right? So each article, and now let's say you as a reader, when you get that book, you don't know which category it came from, who was the sub-editor who actually created that article. All you see is a collection of articles, right? Now, as a reader, can you group these articles by their type? In fact, what you really want to do is, can you infer the type, one of these types, based on reading all the articles, right? So this is what we call, and we'll look at it maybe next week or even on Friday, latent variable modeling, right? Latent means hidden, of course. So you have some data points. Each data point has some hidden variable, right? Which is, in this case, the office that it came from. Did it come from sports or health or politics or technology, right? You don't know that as a reader, but can you infer that by looking at the data, right? But before that, let's talk about a simpler problem, which is you look at these articles and can you group them together, hoping that each group would correspond to the office, right? So that problem is called clustering, right? So again, idea is simple, grouping similar things together. However, what this simple definition includes is this notion of similar, like what is similar, right? So there is an implicit notion of a similarity or a distance metric. Actually, there is an explicit notion, right? So you need some metric which can compare these two, and then you can do this clustering, which is an unsupervised learning task. All right. So the idea is this. Let's say this is your data, right? Each data point is a magazine article. Let's say somehow you have been able to represent each article using two features, maybe just counting the number of images that they have and counting the number of words that they have. That's just for sake of argument, right? So let's say the data looks like this. Now, as a clustering algorithm, your task is to color them with 4 different colors, all right? Such that, hoping that all the red points will belong to one semantic category and all the black points to something, and so on, right? So that is the task of clustering. Now, there are many methods available, many clustering methods in which you feed these data points and they will output these colors. All right. So we will look at one of them, which is called k-means, which is one of the most simple but also very effective, right? Very effective, and it works pretty well. So we'll look at that. But if you're interested in more clustering methods, then you can go explore on your own. But the clustering, the only one that we will talk about is k-means clustering. So our objective is that we are given some n data points. Each data point is expressed in some d-dimensional space. For example, here the d was 2. We are representing it in 2-dimensional space. But in general, you have d-dimensional space, and you want to group them in k clusters. All right. So here we are saying how many clusters you want. So in this case, maybe what I would have expressed was, I want to group these points into 4 clusters, right? So now I'm going to show you the k-means clustering algorithm, which is pretty simple, and a lot of you might already know it, right? So what you do is you start with some k randomly initialized points in this d-dimensional space. This k should actually be uppercase K. So you start with k points, and we call them cluster centers. And then this is an iterative method. So in each step, what you do is you take each one of your data point and you find out which is the closest cluster center right now, right? Which means that you will use your distance metric, right? And then, then you recompute the cluster center. And then you keep repeating this until you converge, right? So that's a general algorithm. So we'll probably, all right, so let me show you a quick demo, and then we can break. Well, actually, let's do it in next class, because I think we are out of time anyway. So basically, what I said so far is that clustering is a general method, which is an unsupervised learning task. And there is one algorithm that we are going to look in a little detail, which is called k-means. And the idea behind k-means is that it does this iterative learning, all right? And then we are going to also understand what it really does. Essentially, k-means tries to minimize some objective function, right? It turns out that this solving this objective function problem is NP hard, which is it requires exponential exploration. But k-means is more of a heuristic, which kind of tries to minimize this. Not guaranteed to reach the right answer, but it is sort of it does pretty well. So we'll look at it, and we'll look at a demo as well on Friday. Any questions so far? Yeah. Yeah. So that's a good question. So in clustering, k is known, which means that I would ask for 4, which is kind of oftentimes a drawback of clustering, which means that you have to know beforehand how many clusters there are. In this data set, it was easy because we could visually see it. But in reality, when you have 10-dimensional, 784-dimensional data, then you would not know, right? So then it is more of a trial and error, and I'll show you how to do that. But then there are other clustering methods which do not really need this. They can work without having to explicitly provide the k. But then they have some other issues. So we'll talk about it as well. All right? Any other questions? All right. Thank you very much. I'll see you on Friday.